it loses all resistance to electric currents. The current then flows through without any loss of energy, and all of it can be turned into work. The only catch is that such superconductivity only seemed to exist very close to absolute zero, say within 20 degrees of it. And although for years, for something like 70 years, we tried to find substances that were superconductive at higher temperatures, nothing ever worked until just a few years ago, when they suddenly found that certain ceramic substances were superconductive at much higher temperatures. And now there's a great push to try to figure out what ceramics will give us the highest temperatures for superconductivity, still low, but higher. And how you can take those ceramics, which are very brittle substances, and learn how to make them wires out of them. Because if we could have, quote, wires, unquote, which conduct electricity without heat loss, we can make electricity do 2 or 3 times as much work as it does right now. There are various other things we can do with superconductivity too. Build still smaller computers, still more rapid computers. We can perhaps use it to create nuclear fusion and give us a completely new source of energy. And it might become possible to create magnetic fields which can be repulsive, which can push things away, so that we have trains, let us say, rolling along a metal railing, perhaps 1/10 of an inch above it, held up by a magnetic field created by a superconductive current, and there's virtually no friction. And if you have it go through an evacuated tunnel with no air resistance either, it can go as fast as an airplane. And you get in, and in a matter of an hour or so, you find yourself going from New York to San Francisco, to say nothing of the fact that the energy we save can be used for other things. Ever since ancient Greek times, scientists have been speculating as to the ultimate structure of matter. What is it that makes up all the various things we see about us? Things that are so different: water, metal, living things. Surely there must be something that makes them all up. And we've worked our way down to atoms. By the beginning of the 1800s, we understood atoms. By the beginning of the 1900s, we understood there were still smaller particles inside of atoms. And since then, we've been trying to investigate these small subatomic particles in order to find out just exactly how they fit together and build up a structure. And the only way we can do that is to smash particles together and observe what happens in the debris that it produces. It produces all kinds of other particles out of the energy of the smash, because, of course, energy and matter are interconvertible. And we have discovered, for instance, that apparently the fundamental particles, the ones that can't be broken down any further, are 6 leptons and 6 quarks. But one of the quarks is still missing. It should exist in theory, but we haven't located it. In addition, there are certain other particles that make it possible for different particles to interact with each other. And one of them is the Higgs particle, so-called because a physicist named Higgs pointed out it ought to exist. And we haven't located that either. And so we need more and more energy to smash particles together more and more sharply and more energetically. And in fact, they're talking about the super collider, which would be a evacuated tube miles and miles across, in which the particles can be circling and circling, going faster and faster, getting more and more energy until they finally smash together. And we'll see if perhaps we can detect the missing particles and who knows what else. Now, not only is this a matter of scientific curiosity, but it's liable to explain to us, for instance, how the universe began. Because when the universe first started, there was a tiny little object, enormously high in temperature. its properties completely different from the universe we now have. We might be able to understand it if we knew more about the ultimate products of matter. And in addition to that, there's every indication that some 90% of the universe we cannot see or sense in any of our instruments. It's called the dark matter because it doesn't glow, it doesn't give off any radiation, and we have no instruments that detect it. If we knew more about the ultimate construction of matter, we might be able to understand what the dark matter is and learn how to study it, and learn about 9/10 of the universe that we know nothing of. And it'll tell us how it developed, where we're going, where we came from. And again, we have no way of knowing how that will help us in our own technology. I mean, when we discovered the electron in 1895, it seemed to be just a scientific curiosity, a tiny little particle that was inside atoms and nobody cared except a few scientists. Except that out of it grew the great electronics industry. Without the electron, we wouldn't have radio, we wouldn't have television, we wouldn't have recording devices, we wouldn't have almost anything we now have and take for granted. And we don't know what further discoveries may tell us not only about the universe, but about our own technology.
Isaac Asimov's Visions of the Future has given you a preview of the subjects and issues the analog science fiction and fact video series will be all about. Look for future videos that will be out soon.